In this lesson, we're going to look at the concept of direct variation, as well as looking at rate of change and initial value. And we're going to look at understanding why a relationship may be a direct variation. Then we're going to look at modeling a direct variation relationship using a table of values, a graph, or an equation. And we're going to solve problems involving direct variation relationships. Our outcomes include, again, explaining why the points should or should not be connected on the graph for a context, relate slope and rate of change to linear relations, identify a linear relation as having a direct or partial variation relationship, create a table of values for a given equation of a linear relation, solve a contextual problem that involves the application of a formula for a linear relation, and write an equation for a given context, including direct or partial variation. Now we're going to concentrate on the direct variations in this particular lesson, but we're going to look at partial variations later on. So what is a direct variation? A direct variation is a linear relationship in which one variable is always a fixed multiple of the other variable. For example, the y value is always 3 times the x value. In a graph of a direct variation relationship, the slope of the line is the fixed multiple. So our slope is the fixed multiple in our relationship. And the y-intercept is always going to be 0 for a direct variation. Our initial value is the value of the dependent variable, which we graph vertically, when the independent variable, which we graph horizontally, is 0. So in a direct variation relationship, the initial value is always 0. So that means that we're at the point all the time in direct variation. We start at the point 0, 0. Okay, so we always start at the point 0, 0, which is called the origin. The rate of change is the amount by which the dependent variable changes when the independent variable increases by 1 unit. In a direct variation relationship, the rate of change is constant. And the rate of change, this is also another term for slope. Okay, so when I refer to rate of change, what I'm looking for in my graph is the slope. So we're going to start with an example here. The dispatcher of a school bus company is monitoring the local weather forecast to decide whether to cancel school buses for the next day. At 9 p.m., there is no snow on the ground, but it has started snowing. It is predicted that 2 centimeters of snow will fall each hour through the night and into the next morning. So the first thing we want to determine is what is that initial value of the depth of the snow at 9 p.m. 9 p.m. is hour 0, or the 0 hour. So our initial value is always when we're at our independent variable, which in this case is time, is 0. And in our situation, we said that at 9 o'clock, there is no snow on the ground. So that means the initial depth, the initial value of the snow is 0 centimeters. So once again, this is a line that passes through the point 0, 0. What is the expected rate of change in the depth of snow? It said in the problem that it is expected that 2 centimeters of snow will fall every hour. So if 2 centimeters of snow falls every hour, that is our rate of change. Graphically, again, that would be represented by the slope of our line. We're going to create a table of values for the first 10 hours, and we're going to explain how our table shows the initial value and the rate of change. So I've got my table here. What I'm going to do is in hour 0, which is 9 p.m., so hour 0, 9 p.m., we have no snow on the ground, so the snow depth is 0. 1 hour later, at 10 p.m., We should expect, if the snow is falling at a rate of 2 centimeters every hour, that our snow depth is going to be 2 centimeters. 2 hours later, at 11 p.m., we're going to have 4 centimeters on the ground. Okay, we can continue this pattern until we get this this table set up here, which looks much nicer than my scribbles. Hour 0, we have a depth of 0 centimeters again. And by 7 a.m. the next morning, which is 10 hours after the snow started, we should see 20 centimeters of snow on the ground. How does our table show the initial value and the rate of change? Well, the table starts at the hour 0. So when we're starting at hour 0, our independent variable is 0. That means our dependent variable is the initial value. So the initial value in this case is 0. And every hour, the snow depth increases by 2 centimeters. So it shows a rate of change of 2 centimeters an hour. If we go from 9 o'clock to 10 o'clock, we're seeing a change in the depth of the snow of 2 units, plus 2. If we go from 10 o'clock to 11 o'clock, we're seeing a change in the depth of the snow by another 2 centimeters, from 2 centimeters to 4 centimeters. If we go from 11 o'clock to 12 a.m., our snow depth is increasing from 4 to 6 centimeters, so another increase of 2 units. So every hour, we're seeing an additional 2 centimeters of snow on the ground. So explain how this shows that the relationship is a direct variation. We said that in a direct variation, our initial value must pass through the origin, and we know that it does. When time is 0, the depth of the snow on the ground is 0 as well. Also, we have a constant rate of change. It's fixed at 2 centimeters an hour. So for every hour increase in our time, we're seeing the amount of snow increase by 2. This amount of snow is always going to be a multiple of the number of hours that have passed. So both conditions, having an initial value of 0, 0, and a fixed rate of change, are met for a direct rate of change, direct variation. So we're going to predict what a graph of the table of values would look like. The first point on our graph should be the origin, 0, 0, and the data will move in a straight line. The slope of our line will be equal to the rate of change. Again, slope is always equal to the rate of change for any linear graph. What time will it be when there are 12 centimeters of snow on the ground? Well, according to our table, there will be 12 centimeters on the ground 6 hours after the storm has started, or the snowfall anyway. If the snow starts at 9 p.m., this means the snow will be 12 centimeters in depth 6 hours later, or at 3 a.m. The decision to cancel buses must be made by 6 a.m. How much snow will be on the ground at that time? Well, by 6 a.m., the snow will have been falling for 9 hours. This means that there will be 18 centimeters of snow on the ground at that time. So here we have another example. Kelly works part-time at an ice cream shop. She writes down her hours and her earnings for each of her first 4 weeks on the job. In week 1, she worked for 12 hours and she earned $132. In week 2, she worked for 8 hours and she earned $88. In week 3, she worked 17 hours and earned $187. And finally, in week 4, she worked for 15 hours and earned $165. So what is Kelly's hourly rate of pay? To find the rate of pay, what we have to do is take her money earned and divide that by the number of hours worked. So if we take the week 1 numbers, her rate of pay, she earned $132 in week 1, and she worked for 12 hours. So 132 divided by 12 is going to be equal to 11. If we look at week 2, week 3, and week 4, we're going to find the same result. In week 2, she worked for 8 hours and earned $88. So $88 divided by 8 hours worked is also going to be $11 an hour. And we do that for week 3 and week 4, we're going to see the exact same thing. So we're going to create a scatter plot of the data, and then we're going to describe any pattern we see in the points. This can be done by hand or using technology. So here's what we should see. We've got our 4 weeks. When she worked for 8 hours, she earned $88. When she worked for 12 hours, she earned $132, and so on. So the pattern we see is that the data seems to follow a straight line path. And as the hours worked increases, so does the pay. So the more hours you work, the more money you get. Do you think it's reasonable to draw a straight line through the points to connect them and to represent the relationship? Why? If it is reasonable, draw the line. So is it a reasonable assumption that we can connect our points here? Sure, it's reasonable. In this case, it's possible for Kelly to get paid for parts of an hour that she may have worked. She might receive a 6.5-hour shift or 3.75-hour shift or any portion of an hour in her shift, and she would get paid for the time she worked. So she doesn't just get paid for it once she passes an hour worked. If she works for half an hour, she'll get paid for half an hour. So yes, it is reasonable to draw a line through our data, so we will. What are the slope and the y-intercept of this graph? The slope will be 11 because it's equal to the rate of change, or our rate of pay, which is $11 an hour. And if you think about it, if she doesn't work at all that week, she's not going to earn any money, is she? So the y-intercept will be equal to the amount of money she earned for no hours worked. This would be 0. In other words, we're at the origin once again. So use the graph to estimate how many hours Kelly would have to work to earn $200. So what we're going to do is we're going to draw a line from $200 extending to our line that we drew through our data. And we see that it crosses the line at approximately 18 hours. More likely it's 18 hours. So it would take Kelly about 18 hours, according to our graph, to earn $200. We're going to explain how the graph shows that the relationship between number of hours worked and earnings is a direct variation. There's 2 conditions that must be met. The graph is linear, that's important, and the graph passes through the origin. The rate of change in this case is again a constant value. What is that value? It's $11 an hour. One final example. Brian owns a repair garage. He has 4 cars scheduled for service today. Brian charges $72 an hour for labor. He estimates how long each job will take using an online automotive database. He estimates that the 4 jobs will take 1.3 hours, 2.0 hours, 1.8 hours, and 2.5 hours. So we want to write an equation to model the relationship between Brian's labor charge and the number of hours the job takes. The data does fit a direct variation relationship, because again, if Brian doesn't work any hours, he's going to earn no pay. He will not get paid for no hours worked, so the initial value is 0. and he charges $72 an hour. That's a constant rate. That's going to be the slope of a line. The equation that can be used to model this relationship is L for the total labor cost equals 72 times T, where T represents the number of hours he worked. So the amount of money that he's going to charge for his work is $72 times the number of hours he has worked. So we're going to use that equation now to determine the labor cost for each of the 4 jobs first, and then once we know the cost of each of the 4 jobs, we're going to look for the total amount of labor charged for that day. So in job 1, we're using the equation L equals 72T. L is equal to 72 times the number of hours he worked, which is 1.3. So he'll charge $93.60. In his second job for the day, it was a 2-hour job. So the amount of money that he charges for labor is going to be 72 times 2 for the 2 hours of that day, or $144. Oops. In job 3, we have a 1.8-hour job. So the amount of labor cost that he charges is 72 times 1.8, or $129.60. And for job 4, it's a 2.5-hour job. So he's going to charge $72 per hour times 2.5 hours, and that'll give him $180. So the easiest way to calculate the total labor he charged for the day would be to take all 4 of those numbers and add them together. So the total labor charge for the day, is $93.60 plus 144 plus 129.6 and plus 180. So he charged for labor costs that day $547.20. Predict what a graph of the relationship would look like. Well, the graph is going to be linear because we have a constant rate of change. The amount of he charges per hour for labor is going to be exactly 72 every hour. And so here we go. And of course, it will pass through the origin because if he doesn't work any hours, he doesn't earn any, or doesn't charge any labor costs. How does the graph relate to the equation? Well, the slope of my graph was 72, just like the rate of change was in the equation. So to summarize this, a direct variation is a linear relationship where the rate of change is constant and the initial value is 0. The dependent variable is always a multiple of the independent variable in a direct variation relationship. The rate of change, we also said, can be referred to as a slope. So it's important you remember that. A graph of a direct variation is a straight line relationship that passes through the origin. And the equation for a direct variation relation can be written as y equals mx. And in this case, m is the slope or the rate of change. So y is dependent on x. As x changes by a multiple of m, we're getting our y values.